Okay, this is Formal Lab 3 by Matthew Hoffman, Thomas Breedlove, Matt Hunter, and Brandon Grimes. So our introduction and main idea, so we really wanted to research bond energies for three different molecules, which would have been nitrogen, oxygen, and hydrogen, and how they related to the energy needed to break the bonds of those molecules interacting with each other. So our punchline is the larger the epsilon or the depth of the well in the Leonard-Jones potential, the higher the bond energies are for each pair of bonded molecules, or in other words, the more energy it would take to break those respective bonds. So for our experimental design, so we really wanted to know how different molecules bond to one another and how that affect the bond energies and the total energy of the bonds. So for this lab, we changed dt, which was the length of our reaction, epsilon, which we said was the depth of the well, sigma, which is the distance between the molecules in their most stable arrangement, and then also the radius of the molecules. So like hydrogen had a smaller radius than oxygen, obviously. And so we kept constant the fact that each particle would react with hydrogen. And the other graph we chose was to create was speed versus time, just to see if the atoms or the molecules were in a bonded state. And we could see this by oscillation.
This is simply just the code we use to find our outputs. These are the numbers we put in. Sigma is measured in picometers and is the distance between the two atoms. Epsilon is measured in joules and is the depth of the well, or the energy that it takes to break the bonds. Atomic mass is just the weight in grams of the substance, and atomic radius is measured in picometers and is just how large it is. Here we have our graphs, which we got from running through the code. The top one is fairly self-explanatory. It's just the energy within shows that there's a total energy of 0 in almost all of the runs. The bottom graph helps us see that the oscillation, or shows you the oscillation. Each spike is one oscillation in this case. The number of oscillations can be increased by changing the distance between the two. The closer they are, the more likely they are to oscillate.
Okay, so our energy graph in the last slide showed a full Leonard-Jones potential graph with both kinetic energy and total energy, along with the potential energy well, which is normally the only part shown in the Leonard-Jones graph. The particles oscillate within a certain bounds of one another due to repulsive and attractive forces on the molecules, and this makes sense with our understanding of Newton's third law, where all forces have an equal and opposite reaction, which is shown by our speed graph. The two equal massed hydrogen molecules both increase and decrease speed equally, while the much smaller hydrogen has such a small force compared to a large molecule that it has very little impact on the speed of the oxygen or the nitrogen atom, while the oxygen and nitrogen atom have a large impact on the hydrogen atom's speed. The total energy of our system is also conserved in order to show these differences.
The simulation has events that are similar to the same events that take place in a Hadron Collider. The objects in the experiment are constantly trying to collide with each other, and they are also constantly repelling each other. This is due to their negative electron clouds, and that is how it applies to the world of physics. The error that could come from our code is if the time of the simulation was too low or too high, the simulation could stop working. It can't simulate all the situations. You have to use proper measurements. You have to make sure that your value for dt is sufficient. The sigma also has to be set within confines. And it is also difficult to factor in all of the variables that are in play in quantum mechanics in a simulation.
Okay, that's the end of our presentation. Thanks for listening.